For the single rigid body creation, at least 3 markers need to be on the object. We do recommend you put 4 or 5 markers, just in case 1 or 2 markers were not being detected during the test. The rigid body will still be there. We also suggest put the markers asymmetric for the better understanding the pose direction that rigid body facing during the movement. We take the smaller drone as an example here and put it inside the capture area as shown. We can see 4 markers very clear in the 3D view. We can click freeze and zoom in. We press and hold the shift key in the keyboard and left click and drag a box to select all of the markers on the drone. Right click anywhere and choose create a ridge. The default setting was single ridge. We can also create multiple ridges at once. Multiple frame ridge can also be created by slowly moving the object. And create a ridge with customized coordinate could also happen here. You can name it and choose the skeleton orientation. As shown, all the markers will be linked. Our software will automatically create a small coordinate system at the center of the mass of the object, and the red cone will show at the origin and the points to the direction we just chose. The red cone is the skeleton, which is just easy for us to clarify the direction that the object face during the movement. It doesn't have any physical meaning. In addition, if you don't want the skeleton at the center of mass, you can click Axis tool. In here, you can move and rotate the small coordinate system wherever you like, which will also affect the positioning information of the ridge when we later monitor and export the ridge data. Next, we can select 2 views at the top. Another view choose Analysis Graphs. Then we can have the live data of the 4 markers on the drone, which include the position, the velocity, and the acceleration. Then we can choose skeleton graphs. The live data will show here, which include quaternion, Euler, Euler velocity, Euler acceleration, translation, velocity, and acceleration. We can also record and cut for the drone movement and see the data afterward. Firstly, we name the cut file test and press record. We let the drone have some movement, include some rotations, and then stop recording. Then we go into the edit mode and find out cut file test1. The afterward number was automatically added when you finish recording. We can see the whole movement and stop anywhere you want by dragging the timeline. There also has some new functions developed. When we right-click the blank space of the 3D view, we can click Show the Marker or Rigid Trajectories to visualize the path. We can also click the Intelligent Agent inside the 3D view to have a simulated dashboard for drone and unmanned vehicle pose information. When we open the second view, and all the data of the marker and analysis graphs will be shown here. If we change to skeleton graphs, we can find all the pose information here. If we go back to the analysis graph, you can see there has some blue squares in the timeline, which means the marker has not been detected at the time. Maybe it was covered or went outside the capture range. If the missing time wasn't too long, our software can help to fix it. You can click and hold the mouse wheel to select the missing area and click cubic joint. It will speculate where the marker should be there. Then go to the skeleton graphs. The skeleton was still missing during the time. We can click Calculation from the top toolbox, which will help you to let the red coin back. But again, these two fixing methods were just a speculation from the software, which not 100% accurate. And then we click Save the capture file after fixing. Then we can also explore the data from the analysis and skeleton graphs. Click File, export the TRC file, and also explore XRS file. The TRC was the marker point position, and the XRS was the skeleton pose data that both can open within Excel. In TRC file, the first column is the frame number. The default setting was 90 FPS. We can see in frame 91 is 1 second. And the second column is time. Then is the timestamp. Next is the XYZ position of the 4 markers. Next, open the XRS file. The first column is still the frame numbers. Then was the timestamp. Next is the XYZ coordinates of the center of mass. And then is the XYZ velocity and the resultant velocity. Same, the XYZ acceleration and the resultant acceleration. And then is the quaternion, the Euler velocity, and the Euler acceleration. Back to the software, the data casting pan is to keep sending out the pose information. The address is to choose you want to send through the wire or the wireless network. The SDK is the data type we're sending out. You can choose different coding languages to receive the data. Next, the VRPN usually go with the rows. Our software can do both rows 1 and rows 2. These parameters you can change based on your need. For example, I'm both sending and receiving the data through the wired IP address way. I will use Windows C++ as a receiver to show how it works. You can see after typing in the IP address and select Passive Receive, the data was successfully got here. When we stop in our software, the data will stop receiving as well. When we look at the casting data, we can see 2 groups of information in one single frame. Upper is the position, velocity, and the acceleration of the 4 markers. And the downside was the information of the rigid body. And the information types were literally the same as we just explored in the XRS file. The data casting can both happen in the live and edit modes.